Hi everyone, I'm on the way to Ada, Oklahoma, the home of GAMI. GAMI created the G100UL fuel. I'm going to talk to George Brawley and Tim Roehl about it, and then we're going to fly the Bonanza with G100UL. Come along.
GAMI and the sister company Tornado Alley Turbo have been around for many years. They make popular products like the GAMI ejectors and the turbo normalizing system for many airplanes.
My first trip to GAMI was about 12 years ago, shortly after I bought the Bonanza, to attend the APS class, Advanced Pilot Seminar, where I learned most of what I know about leaning and running the engine. And I remember from this visit the engine test stand that they built quite a while ago, and that provides instrumentation to see a lot more data than we can see on our engine monitors. So we're going to see a side-by-side comparison, 100 low lead and G100UL on that engine test stand.
Wide open throttle, lean of peak. That has become the cruise power setting of choice for many graduates of the APS class. But recently, the thing we hear about GAMI in the news is their unleaded high-octane fuel, named G100UL. Tim Roehl is the president of GAMI. I asked him how the company decided to start development of the unleaded fuel.
Since we acquired the STCs for the turbo normalizing systems in 1998 and started Tornado Alley Turbo, we had a concern for what the industry was going to do with respect to a future high-octane fuel. The industry was gravitating towards a 94UL as a replacement fuel. We realized that that fuel was not suitable for even high compression ratio naturally aspirated engines, let alone turbo normalized engines. And so we got very focused on trying to make sure that the industry transitioned to a high octane fuel. We knew a better fuel could be made than the 94UL. We had seen some examples and done some testing here. But we decided that we probably had to take the bull by the horns and see if we couldn't develop a high octane fuel.
Tim leads the business side of GAMI and Tornado Alley Turbo. His counterpart on the engineering side is George Brawley. I first met George when I attended the APS class. Even back then, we got a tour of their engine test stand, named after Carl Goulet from Continental Motors. Here's how that came about.
And it's interesting, it was a suggestion made to us by a guy named Carl Goulet. Carl had retired as the vice president of engineering at Continental back in about 1992 or 3. He looked at me and he said, "George, you guys need to build an aircraft engine test facility." I said, "Why do we want to do that?" He said, "You won't believe how much you will learn by being able to do that."
And learn they did. A lot of their findings helped with product development, tests, and certification, but it also created the foundation for the APS class. More recently, the test stand was instrumental in testing the G100UL fuel. One of the many things they can reliably detect and document is detonation. After all, one of the key concerns with a new fuel to replace 100 low lead is how well can that fuel protect an engine from detonation?
And pumping, we got 11, we got plenty. You ready?
Yep.
Thank you.
The upper half of the screen is what we call a point cloud. And each one of these little dots that you see right here represents a single combustion event. And the magnitude vertically on the vertical axis corresponds to the magnitude of any detonation event. And you know, anything below about right here is just noise and random stochastic combustion stuff. But when you start getting above this level and getting higher, it starts to be either incipient detonation or real detonation. And if it gets up into this level, up in here, then it's significant detonation that's represented by each one of those combustion events.
So now we have a happy, healthy engine.
Oh yeah, well, it is just idling though. But there's like 2 minutes of data from left to right here. So we're going to power up a bit.
So they run the engine at a high power setting and alternate between traditional avgas, aka 100 low lead, and G100UL, looking for any measurable differences in temperatures, pressures, and, most importantly, detonation.
And Martin, right now I'm working on this screen up here. And the one over here on the right here is the prop control in blue. And the one on the left in gray or black is the throttle. So I'm trying to play with the engine controls to get an operating condition that simulates that in cruise. If you'll look down in this lower right-hand box, it says EGT TITs. You'll see all the EGTs and a TIT. You can ignore the TIT, but I'm slightly leaning the engine, reducing the fuel flow, and I think those are still going up a little bit. Yeah, right there on the left-hand side, which is where the newest event is. Yeah. So we're getting closer and closer to peak EGT, just like you would do in the airplane, leaning the mixture. And watching and there it just peaked over and started down. So we've got a fuel flow of 15.7 on this big engine, and I'm going to make it very slightly richer to get it back to peak. So now let's switch to G100UL.
Okay, ready?
Yep. Had air in the fuel line. It happens sometimes when you change from the left tank to the right tank. So we're now running on G100UL, which is what's showing right there. And over here is still the 100 low lead data, and you can tell there's essentially no difference in the data whatsoever.
Right.
Here's what detonation would look like if it were occurring. But no matter how hard we pushed the engine in this experiment, there wasn't any detonation with either G100UL nor 100 low lead. So it sure looks like we can eliminate the lead from aviation gasoline without sacrificing detonation margins. But does that mean we have to?
Honestly, I don't know. There's not that much lead left in the world ever since we got rid of it in car engines. However, we may not have a choice, right? And there's only one plant left in the Western world that makes the lead additive for 100 low lead. It's in the UK. If one day they decide to go out of production, well, that will be a bad day. So I think it is a good idea to be proactive about it. You know, phase this in, or phase it out, phase the lead out at a pace that we control, instead of one day waking up and having a big problem and then trying to do it in a rush.
So it's all about detonation, but what exactly is that? And how has lead prevented it so far? I asked George to explain this.
So the process of detonation, the best way to describe it, is that you've got, as these flame fronts advance, you've got unburned air and fuel, some of which, for example, is up against the aluminum cylinder head on the inside of the combustion chamber. And so if the cylinder head temperature is pretty hot, it's transferring heat into that unburned fuel and air charge in a little pocket of there. And then the flame fronts, the progressing flame fronts, they're giving off an enormous volume of infrared energy. And that infrared energy is bouncing all around through all those little pockets of unburned fuel. And if the pressure's high enough and the local temperature of that pocket of fuel is high enough, instead of burning, it detonates and explodes. And when it does, it sets off a shock wave inside the combustion chamber, which travels at the speed of sound across the combustion chamber. The speed of sound at 3,000 degrees, which is about the ambient temperature, which is very much faster than the speed of sound on a standard day in the atmosphere. And that shock wave is what is like ringing the bell, and it causes the detonation or the characteristic sound of pinging that people used to hear in their cars all the time back in the 30s, 40s, and 50s. So the question is, okay, how does the lead affect all of that? Well, some claim it slows down the combustion process. I'm not sure that it's not something where the molecules of lead are not absorbing some of that infrared energy and keeping the remote pockets from getting as hot as they might otherwise get. But the reality is, I don't think anybody could, with a straight face, fully declare that they absolutely know the complete answer to a question. Empirically, it works awfully well. Because of the public disinformation that was blaming the problem at UND on the absence of lead. We've got to have the lead because it's going to somehow or another magically lubricate or cushion the valve seat. You know, lead inside the combustion chamber is in the form of lead oxybromide because it reacts with the scavenging agent, which is ethylene dibromide, and it forms lead oxybromide. It's a nice abrasive, you know. You could probably make a fingernail file out of the stuff.
I'm not a chemist at all, but I'm surprised how often I hear people say, well, isn't lead needed for lubrication? And
so
that's one of those old wives' tales, I guess.
Yeah, it is.
So if between 100 low lead and G100UL there are no differences in detonation, what other differences are there?
When you go to the fuel pump to buy a gallon of gasoline, what you really are trying to buy is energy, BTUs per gallon.
Yes.
And this fuel that's in the UL, the G100UL side, on a volumetric basis per gallon, has 3%, 4% more BTUs per gallon than the 100 low lead does. And so when you're running with a lean mixture, by definition, there's more oxygen molecules in the mixture than there are hydrocarbons to consume the oxygen molecules. And so when you add a little more BTUs, they get to combine with still more oxygen molecules, generate a little more heat during each combustion cycle, and it makes more horsepower. The only other thing that you can tell for a difference in your airplane, single engine Bonanza, right?
Yes.
So when you lean the mixture and you watch your engine monitor and you go through peak, you do that on the 100 low lead, you go back and do it again on G100, and you do it 2 or 3 times on each. And you very carefully note the temperature at which the first cylinder hits peak. What you'll see is that typically at peak, the exhaust gas temperature will be anywhere from 10, 15, outside 20 degrees higher than it will on the 100 low lead. Now we're talking about at peak the difference between 1450 and 1460, or 1450 and 1465. There's a perfect explanation for that, and that is that the G100UL does in fact burn very, very slightly slower than the 100 low lead does, which then results in a little larger fraction of the fuel that has not fully been consumed that goes out the tailpipe, and therefore influences because it still has some flame activity, it influences the temperature on the exhaust gas temperature probe.
So how about peak pressure? Is there a difference?
They're virtually identical. Typically the peak pressure will be very slightly lower and very slightly 1 or 2 degrees further after top dead center. You know, if top dead center is here, combustion chamber is coming up, the spark happens here, the pressure goes up, goes through top dead center, the piston starts down, pressure still goes up, and then it starts down. That interval to peak pressure is something that we've characterized as the angle theta to peak pressure, the angle theta from top dead center over to peak pressure. Let's say on the 100 lead it's 15 degrees, on the G100UL it might be 16. But the peak pressure will be, you know, if the peak pressure on the 100 lead is 800 psi, the peak pressure on the G100 might be 760 or 770. But because the horsepower is not a function of the peak pressure, but it's a function of the integral under the two pressure curves, they end up making the same horsepower.
Leaner peak, I fly a leaner peak almost all the time in cruise. Small differences, like you said, but I might see a little bit more range or a little bit more speed if I fly at the same fuel flow. How about when I'm richer peak for takeoff and climb? Is there any difference there, or?
Again, it's extraordinarily subtle, but yes, because there's a larger volumetric energy content, if you wanted to set the mixture at 3% lower or 4% less rich than you do on the 100 low lead side, the engine would perform identically with respect to the thermal characteristics and the cylinder head temperatures.
Okay.
But if you're running, you know, 26 gallons an hour on takeoff and early climb, you know, what's 3% of 26 gallons an hour? It's, you know, 4/10, 5/10, 7/10 or something of a gallon. So you might save that much in the climb.
Small changes, but it sounds like the way I fly my engine, everything is just a little bit better.
We're
than
going
it
to,
was.
5 years from now, the pilot population is going to look back and see things like this video and say, what the heck was all the fuss about? You know, my God, those guys were going on endlessly about changes that nobody really cares about.
Yeah.
By the way, both Tim and George are active pilots themselves. They don't just build turbos, tip tanks, fuel injectors, and make the fuel. They're also passionate about flying the same kinds of airplanes many of us fly.
George was an active flight instructor and had his own airplane at the time, and I was able to get my private pilot's license, mostly in his Bonanza while we were going on various trips. Got my instrument rating and have enjoyed, you know, flying mostly recreationally. We bought a 1956 T-34 in 1998 and did some good on the T-34 group. You can see we're fans of T-34 aircraft and developed some AMOCs for them. So right now I think we've got 4 Bonanzas and a T-34, and most recently acquired a real gem of a 1947 Bonanza Model 35 that we're going to kind of bring back to life, that was actually kind of languishing here in Ada.
Then it's time to put some G100UL into my Bonanza. But there's another airplane ahead of mine. It's my friends Kim and Doug Rozendaal from Iowa in their rocket. None of us knew we'd both be here on the same day. Doug has been using G100UL in multiple airplanes, including his famous Mr. Mulligan during airshow performances.
So I'm here in Ada today. I picked up a tank full of G100UL fuel. This is the 3rd time I've run G100UL in my F1 rocket. It's got a 10-to-1 Lycoming 540 in it, so it's high compression. And the only thing I can say about it is it runs just like 100 low lead. The only perceivable differences are the fuel flow is down about 0.3 of a gallon, so instead of 12.5, I'm about 12.2, and the EGTs, near as I can tell, might be up maybe 10 degrees. But it's a seamless transition. I've run pure, I've run blends, I've had 100 G100 in one tank and 100 low lead in the other, and switched back and forth, and it just works. I've also flown G100UL in my airshow airplane, Mr. Mulligan, which is a replica of a Golden Age racer that has a Pratt & Whitney R1340 on it, supercharged. And again, the same results. It is, I don't have fuel flow or accurate EGT in that, but the airplane runs great. There's no perceivable difference whatsoever. I'm very comfortable with it.
Now it's my turn. I had run my left tank down to maybe 1 or 2 gallons on the flight to Ada, so it is practically empty. My right tank still has plenty of normal avgas, 100 low lead. The plane gets a top off on the left side with G100UL. If you look closely, you can see the green color of G100UL. Here's a better view when I take a fuel sample before my flight. The fuel in the right tank has a blue tint. That's your normal 100 low lead. The fuel in the left tank looks green, so that's G100UL. And then it's time for me to fly.
So what I'm going to do today is I have 2 different fuels. I have in my left tank G100UL. That's the tank that's active right now. And in the right tank I have 100 low lead. The Bonanza has a fuel selector, and I have to select the left or the right tank. There's some other airplanes that can draw fuel from both tanks that would result in a mixture of those 2 fuels, but here in the Bonanza with that fuel selector valve, I can control which tank, so which fuel is used at any given time. And the plan is to take off with G100UL. It's a fuller tank right now. I got 40 gallons of that here, as opposed to 28 of the left and the right tank. And then once I'm established in cruise, I will switch between the tanks, leave everything else unchanged, and just observe the difference in performance and temperatures. Ada traffic, Bonanza 0 Tango Bravo, departing runway 18, leaving the area to the north. Ada, clear, clear. Right, line up. Throttle all the way in, all right rudder. Oil temperature is good, CHTs are good, airspeed is alive. And here we are airborne with G100UL. Positive rate, gear up. Climbing through 5,500. I'm maintaining the EGTs per my normal procedure. And our temperature CHTs are just like I would expect them for the climb. We see my left fuel quantities going down. That's consistent with consuming fuel from the left tank, the G100UL tank. Okay, I'm now level at 11,000. The next thing I'm going to do is re-establish peak and go about 20-30 degrees lean from there. So I'm enriching the mixture, get on the rich side, and then start the leading throttle over very slowly. Looking for my number 6 still under the peak. 1472.
We have with the Kelly 25.
Looked like that was the peak. I'm going to 1452.
Kelly 15, gain device fixes.
Or thereabout. 12.1 gallons per hour. 12.1.
Kelly 23, squawk VFR, free change.
Somewhere in there. We'll let that stabilize.
VFR, free continue cruise. Have a good one. Kelly 23. Alright,
we've been on this for 5 minutes now, and we're seeing 135 knots indicated, 165 knots true airspeed. Time to switch tanks. We're keeping everything the same. Fuel flow 12 gallons per hour. 12.0, 12.1.
Slow approach number 5051, 10,000.
We'll give it 5 more minutes and see what
And
happens.
there 5051, Pulse approach 10.5 discretion, maintain 6,000. Discretion is 6,000, Endeavor 5051.
Can see the indicator airspeed starting to come down a little bit. 2 minutes into running on 100 low lead.
600 Papa, 2,600 climbing.
We're approaching 5 minutes on this tank, and indications are stable here. 133, true airspeed now 163, so yes, 2 knots less. We switch back to the G100UL, and we'll give it 5 more minutes, see if the speed increases again. Alright, approaching 5 minutes here on my timer on the Aspen, back with G100UL, and we're back to the speeds before. A hair over 135 indicated, 165 true airspeed. So it seems to be a repeatable experiment. The next thing I'm going to do is I'm going to try to see if a slight reduction in fuel flow by 3 or 4 tenths of gallons per hour will take me back to the 133 knots indicated airspeed, so to the same horsepower output of the engine that I had before. So I'm going to reduce my fuel flow just a little bit here.
Is Echo now, current Riverside, Delta number 2983.
11.7, 11.8. So 3/10 of a gallon per hour less than what we had before. And we'll give that 5 minutes to stabilize and see what airspeed we get. Alright, 5 minutes have passed, and look at that, 133 now with G100UL at the reduced fuel burn. So that's about the 3% difference in energy that you get out of a gallon of G100UL. So, yeah, the results match exactly what George had shared. My CHTs are nice and cool. EGTs are where I'd expect them to be right now here with this mixture. And I'll enjoy the rest of the flight home. I hope you got something out of this. I look forward to seeing G100UL here, hopefully in distribution soon. And just thanks as always for watching. If you like this video, please hit like and subscribe to the channel. That helps me grow the channel. Special thank you as always to my supporters on Patreon. Thank you. You all help make this work possible. Take care, bye bye, fly safe, and see you soon in the next video.